Be it Burj Khalifa, the Pentagon, or your house, the weight of these structures is ultimately borne by a structural element called a footing.
A design mistake in the footing can result in the collapse of the whole building.
Which is why a proper foundation design is crucial. Footings are the most important part of the foundation.
Their job is to distribute the heavy load of the building, concentrated on the columns, to the wider surface area of soil,
to achieve structural stability. Let's analyze the importance of footings and their different types.
Come along. Before understanding the design concept of the footings, first, you need to learn something about the soil. Engineers should analyze whether the soil at the location can bear a calculated amount of load. If the soil is compressible under loading, excavation is done until you find the incompressible layer. This incompressible layer can stand the loading. The plate load test on this layer is not causing much compression. This layer of soil, in civil engineering, is called hard strata. On this hard strata, we can add columns to transfer the load and cover the pit with soil. The soil should bear the entire structural load easily.
However, this concentrated load on the columns will cause excessive stress in the soil due to lesser contact.
If this stress exceeds the soil's bearing capacity, it will undergo the punching effect.
This leads to imbalance in your structure, causing cracks or even failure of the whole building.
To avoid these failures, you can increase the contact area between the soil and columns. Let's introduce a plate member, the footing, at the base of the column. The load will now be evenly distributed on the soil through plate members. This increased contact area reduces the stress on the soil,
and the building stands strong. A structural engineer's job is to find the footing's area and thickness.
These two factors are determined according to the soil's bearing capacity and the building's weight. We have already seen the importance of the footing area. More the building's weight, wider the footing should be.
Additionally, if the structure faces lateral forces like winds or floods, footings help the building avoid sliding due to frictional resistance between the footing and the soil. Now, let's consider the second design aspect, footing thickness.
The footing must withstand pressure from the soil. If its thickness is inadequate, the footing will bend
due to the soil applying uplift pressure on it. This effect is called applied bending moment.
You can see this effect in this FEA result here. To prevent this, the plate's thickness is increased.
There you go. We have designed a stronger and safer footing for our building. This type of pad or isolated footing supports lightweight houses on soil with medium strength. This design can be further optimized economically. The pressure from the soil on this area is uniform. However, applied bending moment increases towards the footing's center. So, central footing thickness needs to be greater than at the edges. Thus, a trapezoidal footing shape is adopted in modern structures for isolated footings. However, a pad-type footing is used in other more complex types of footings.
Suppose your building's columns stand exactly on the property line. Your neighbors won't allow extra space.
Simply to extend the footing. The column is placed on the footing's edge, causing unbalanced loading transfer, or eccentric. This footing can carry a considerable amount of load on the structure.
However, if the load increases too much, the structure may fail. The trick is transferring the excess loading
into another adjacent footing with good strength. This transfer is done by placing a connecting beam in between,
which acts as a strap. One column in this strap footing will generally have an eccentric footing.
Moreover, in some cases, when columns are too close, engineers purposely combine the footing In most modern heavy buildings, the structure's columns are provided with combined footing as a whole. A single reinforced concrete slab is made for each column. These footings are called raft or mat types.
They spread the load evenly from columns or walls on the soil. This footing avoids deep foundations, which would otherwise go 60 to 200 feet deep. In expansive soil areas, the raft foundation is a boon.
That lessens differential settlement. The Burj Khalifa uses a combination of raft foundation and piles,
which forms a combination of shallow and deep foundation. We'll learn more in the next video.